afternoon. I'm Rick Roush. I'm the Dean of the College of Agricultural Sciences. We are delighted to have you all here with us today for our June College Connections webinar. These webinars are designed to give you a unique inside perspective of the diverse programs, people, priorities, and partnerships within the Penn State College of Agricultural Sciences. We are recording this session and will be sharing it via email with all who registered. You can also find links to all past sessions and registration information for future events on our college website by searching by Google or other browser for College Connections. Today's session is Research on Automation and Robotics in Agriculture. I am joined by Dr. Long He, who's an assistant professor in the Department of Agricultural and Biological Engineering. Long will share his research in agricultural machinery and automation, including robotic solutions for agricultural application, precision crop load management technologies for tree fruit crops, and sensor applications in agriculture. Long will be focusing on specialty crops, that is to say, fruits and vegetables, not broadacre crops like corn or soybeans or forestry. After the presentations, we will have a question and answer session, first addressing those questions that were submitted during the registration process. If you have questions during the presentations, please enter them in the Q&A link, not the chat, because it is easier for us to track them there. So without further delay, I'd like to introduce Dr. Long He. Long He works out of the college's Fruit Research and Extension Center in Biglerville in Adams County, from which he's connecting to us today. He received his PhD in mechatronic engineering at Yanshan University in China. Before joining Penn State, Long worked as a postdoctoral research associate at Washington State University and at UC Davis. So off to you, Long.
Thank you, Dean Roush, for the introduction. Anybody can help me? Oh, thank you. So good afternoon, everyone. Today I'm going to talk about some of my research program on the automation and the robotics in agriculture, and specifically for the specialty crops. So there are some motivations for why we need to do this research. So you can see the special crops actually take almost half of the value to the of the all American crops to the U.S. economy. So it's about $79 billion annually. So for particularly, let's see what the cost for the production. I take Apple as an example here. So you can see that the big portion of the cost is the labor cost. And the next is the chemical cost. And there are also other like land and other cost equipment. I didn't put water here, but water is also another part of the cost. So what we can do, and then I put some facts and then the solutions here. So everybody may be already kind of aware that human labor is in a shortage and also in a higher cost. So we need alternative solutions to address the agriculture industry challenges. And also we found that more population need to be fed in the next decades. And that means more food need to be produced. And we have challenges in the limited resources like land and water and so on. Meanwhile, we have excessive application of water, chemicals, and fertilizer in the conventional production operations. And how we could actually to reduce those in order to also reduce the resource use and also reduce the environmental impact. So robotics and precision ag are the key for the sustainable agriculture. So for agriculture, robotics and automation has been actually widely used or some adopted in agriculture. You can see from here, like from autonomous tractors for various field tasks. So tractors has been used for many years. But recent years, autonomous tractors has been introduced in the market and can be used for different tasks in the field. Actually can reduce, kind of increase the efficiency and production. And then you can see the second one is unmanned aerial vehicle for spraying. So that is also another example of showing automation helps to increasing the farm efficiency. And of course, also the automation robotics can be has been used for animal agriculture as well. You can see the robotic milking system, and also like other robotic system actually used in the animal facilities. And also, there's a lot of more robotic system has been under development and testing. Here, just take some examples for apple harvesting, but there's many more. There's a different type of robotic system been testing for crop harvesting, pruning, and other kind of field operations. Here, let's like 3 different type of robotic harvesting systems here for the apples. There's from different companies and the universities. So there's many more under development and testing. Hopefully, there are more in the market very soon. So what are the core components in those robotics and automation systems? So first, I want to point out agriculture system actually is one of the major part, right? Because we're talking agriculture system. In order to implement robotic system and other automation, we need to also think about using advanced agriculture system management. Here, the picture shows a 2D dimensional tree structures that act for apple orchards. That making this kind of tree structures, it will make it possible for robotic system to access to the fruits, branch, and other type of object easily. So this is the kind of the first step to adopt a robotic system and some of the automation system for agriculture applications. There, of course, there are many more, like right now you can see those using like aluminum beds for mushroom production. And there's also some of the hydroponic system for vegetable growing. So those are also for like how to advance agriculture system management in order to adopt machinery, automation, and robotics. Vision system is another one. So because for all agriculture operation, we need to target for certain objects, no matter for harvesting and pruning, we need to target fruits or branches. So first thing is we need to see them, we need to detect them and to find them where those are, and we can next to do the operation. So vision system is the first step. There's a lot of research has been done for the computer vision, for object detection for agricultural purpose. And in recent years, artificial intelligence, especially deep learning models, has been introduced to agriculture field, and that makes object detection and identification much easier and with high efficiency. I list one example here as one of the we did for a disease detection in the tree canopy. So you can actually first take a lot of images, because for this type of study, we need to have a lot of images. And then we'll label them and train them. And then with training and learning the features of those objects, like the color, the shape, and other textures of those objects, we can learn, the computer can learn which are those objects, and then eventually we'll come up with models that help for automatically detecting those objects in the future using robotic system. And then is the robotic manipulation. That's once you detect objects, you need to reach them. So how to reach them? And with the agriculture environment, it's pretty unstructured and also complex. So it's very important to using very proper manipulators to reach to the objects, and also then pathfind how to read them. Those are the acquisition development for reaching objects. Here I list a few kind of examples, the different type of robotic manipulators. So it really depends on what kind of task operation you need, and then we can select optimal ways to do that. Next is the end-effector. End-effector is a kind of mechanism that actually do the actual work. So it's either picking fruits or remove the mushroom or cutting the branch. So it's a kind of mechanism that actually can finish individual or specific task. I want to see another component is called sensing system, because sensing is very important for precision ag, and precision ag can be very important for automation as well. So here, I list a few sensing systems here for like remote sensing and also some in-field sensing system. Just example here. The first one is a satellite imaging. So you can use satellite imaging to identify large-scale crop field conditions, for example, water stress or other kind of fertilizer application. Those can be used for a lot of applications. And then also you can use the unmanned aerial vehicles like UAVs for scouting the crops. Those can get a lot of information from onboard sensors, cameras, and also have the proximal sensing using the platforms driving through the field and taking the information as we need it. And also have some in-field sensing as well, so you can place the sensors in the field. So gather all the information, those can be called a big data of agriculture. So you have a lot of data to present the field and the crops, and how to use those data that we need a decision support system that can actually utilize those data to come up with strategies to manage the crop. Internet of Things is another technology can be used for precision ag and automated applications. That is, IoT is more like connecting all the physical system and also data through the internet that can be used for remote accessing the data and also for automation. So those are the major components for the robotic system and automation. And next, I'm going to introduce some of the research project that we have done in our group here. The first one is robotic crop load management. I'm going to explain a little bit of what is this. So for apples, for example, if we don't do anything on the apple trees, then we'll have much more fruits on the tree than we need, and then it comes at the end with very small and a lot of small fruits. So it's not what we want. So we should start to match the crop load at the beginning. So it started from the dormant season for the branch pruning, and then during the blossom stage, we are doing the blossom thinning, and also for the green fruit thinning stage, like when the fruits are close to 20-30 millimeter, there's another called a green fruit thinning. And eventually, if we do everything right, we can get nice and high quality fruits to harvest. So we have been working on those three types of crop load management system. I will start with the robotic pruning here. So those are the two types of robotic system that we developed for the pruning. The first one is called Cartesian robotic system. The Cartesian system is like three dimensional linear actuator. It's manipulated with X, Y, and Z linear motion, and then we have the end-effector model at the end of the end-effector, the manipulator, and then we can test. We tested this whole system in the field and cut it to 1-inch branches at multiple orientations. And later on, we also trying to attach this end-effector cutter to a 6-degree freedom robotic arm. This is more like industrial type of robotic system. And we also generate the path to target the branches. But this study is still going on, so we haven't do fully automation yet. We have been working on the path generation and end-effector development. The second one, as I said, is like at the blossom stage, like flower stage. So first thing, if we need to thin the flowers, then we need to see them. So using the machine vision system, we're actually trying to identify the flowers and flower clusters in the tree canopy. And for this study, we're trying to using a target sprayer system to spray the flower clusters that actually we as a target to thin the blossom to reduce the number of the final fruit sets. And here's we did using deep learning algorithms to identify flower clusters. For example, this one, if we identify these 4 clusters in the field, and then we're using the develop robotic system to torque those clusters to spray them with the chemical thinner. So you can see from there, we only spray those torqued flower clusters. You can see we can save at least half of the chemicals with if we spray with this kind of precision. So it is very important to get the flower to get identified and then using the robotic system to spray more precisely. And then the next one, if we still have too many fruits after the blossom thinning, for example, then the green fruit thinning is the last step. We can adjust the fruit crop load. The same idea, like we need to identify the fruits and the clusters, right? So we also use the machine learning method, that the deep learning method I introduced earlier, that we are going to using mask assay type of deep learning algorithm to identify the fruits and stems. So with this, we can know where are those fruits and eventually know how many fruits in the cluster and which one we should remove. Because typically we want to keep the bigger ones on the tree, but then remove the smaller ones. So it is important to get the location, sizing, and orientation of those fruits. We did some tests in the field, developed a kind of mechanism to remove the green fruits. Later on, we also adapted this to a robotic arm and trying to using robotic system to remove green fruits. This is the study results that without vision system involved. So we have pretty good success rates if we only consider mechanical parts. And then in 2022, we start to integrate with the machine vision system that actually can sense in the tree canopy and find out the fruits locations and then generate the paths for robotic system to get reached there. I don't have the results yet, but that is something we're still working on. Okay, that is the whole thing is for the crop load management. I will introduce a few other projects that we are involving kind of robotic system and precision agriculture. One is we did some study on the robotic harvesting. We developed two types of end-effectors and using the Cartesian robotic manipulator that we find it is very important to have certain kind of motion to remove fruits because you want the fruits get removed without damage and also have the stem stay on. So the motion and mechanism of the end effect is a key part of that. So that we didn't do too much, but we mainly working on the end effect and the motion part. Robotic mushroom harvesting. So this is a project we have been working a few years and also in the next few years working on this as another project. So first, we would like to test how to remove a mushroom like sufficiently. Like mainly, we're trying to mimic human hands to move the mushroom and then record the motion or an orientation of the motion. And then we develop this end-effector kind of mechanism trying to do what we received from the dynamic motion study. And then we develop this system and put a prototype together and then can remove the mushrooms from there. For the precision ag part, we are mainly involved in two parts of the study. One is for irrigation, that is for precision and an automatic irrigation system. This system, you can see that is we're using the water, the soil water moisture sensors as actually installed in the field. You couldn't see there, but then we have the data loggers or other controllers built together, and then we can actually access the data and control the water, the valves automatically. It can save water and human labor. So this is the interface that we built together that is using the Internet of Things technology, and then we can monitor the soil moistures in the for those sensors in the field. And we have the valve control as well that can be set remotely control or automatic control based on the threshold we're setting for the soil moisture. And it has the historical data and the real-time data to show the soil moisture in the field. So this is example of how we can using the sensing and IoT system for the precision agriculture applications. Another example for precision irrigation, precision agriculture is for spraying. So for the orchard applications, we normally using L+ sprayers. So normally you can see the sprayers, if we don't have any control, actually a lot of chemicals are sprayed in the air or on the ground. So there's a lot of waste there. So how to kind of reduce those kind of chemical waste and more concentrate only on the canopy, but not on to other part of the like the air or the ground. So a precision spraying system was developed using a LiDAR system here. So if you have a LiDAR sensor here, it can detect the canopy with this kind of point cloud. And then you can calculate the density of the point cloud. That can represent the tree canopy density. And based on that, we can spray with the control of the nozzles to spray accordingly. That way, we can save a lot of chemicals. For the previous study we did, we can save at least 50% of chemical, especially for those trees has big gap, and then those empty spaces don't need to spray. And this part is we also consider about adding another part into the sprayer is called inlet air flow control, because when the drift is a big problem sometimes. So if you have big air flow coming through these nozzles, then the chemical can spray to very far and can be can cause a lot of drift. So we adding this average damping system control to control the inlet air flow. And you can see this, we can have different sizing of the inlet air flow. So with that, we can reduce the chemical drift. And also UAV has been also attract a lot of our attention as well. We used UAV using different cameras, like the regular RGB camera, also have multi-spectrum camera to help for crop health scouting. You can see this one is if you want to see your crop coverage, like what the canopy areas are and the density and everything like that, we can using the UAV to scan with very fast speed and efficient way. And also for disease detection and crop healthy monitoring, that using UAV is also a good option. So that's pretty much all the research project that we have been done in the past few years. And in the last slides, I would like to, this slides want to see some of the challenges and opportunities for integrated robotic crop production system. The challenge I want to see is kind of in 3 different areas, like biological systems is more like in the crop system. So agriculture is very complex and unstructured environment. So the uniformity of the crops field cause a lot of challenges for robot and crop interaction. And then environmental challenges. So for example, the wind condition, the weather condition, and lighting condition, those kind of challenges can affect the application as well. And then finally, the technical challenges. So for the robotic or mechanical system itself, we need real-time applications. So that means we need to have high process speed, and then we can come up with the real-time application. The high accuracy, we want to comparable to the human, for example. So we need to be in high accuracy to detect objects, to run the operation of the robotic arms. And then comparable efficiency. So efficiency is very important because we need to get the work done in a kind of short window, and the speed is very important, and then the cost as well. So we need to compare the cost with the human labor as well. But also, of course, those challenges, but we can come with those challenges, we have some opportunities for further developing integrated robotic system for the agriculture. So first, we need optimizing robotic technologies by have the better design of the robotic end-effector, but have better algorithm for robotic system control and for the computer vision system. And think about also for the cost-effective robotic system development, how to reduce the cost, how to get more affordable to the regular growers to using those technologies, and eventually to integrate the robotic system together, like using robotics, precision techniques that like I mentioned before, using robots, and also the sensing information that we received from the sensors, how to send the robots to those with those decision support system, and then have the kind of to finish the task. So those are come with the idea for the sustainable agriculture. So eventually we want to develop a competitive and a sustainable agriculture system for the industry. So for in my program that I have been collecting with collaborated with so many of the faculties and scientists within Penn State, and also without also beyond Penn State. So here are some names that list here that has a variety of expertise. For example, in the horticultures, plant pathology, entomology, and then plant science, and other also some engineers. So there's a lot of collaborations between myself and those folks there, and have a lot of collaboration with the extension educator as well. So there's some other collaborations like beyond Penn State. Have been working with Washington State, Cornell, and University of Maryland, and also USDA folks for those projects. Yeah, I think that's all for my presentation. I will have time to take questions, and I will discuss more on the details. Thank you.
So thanks a lot, Long. That was terrific. It really shows there's a lot of technology being adapted to try to meet these labor and precision needs in agriculture. So we had one of the big questions. We had a number of questions submitted beforehand relate to the big issue of costs. So how possible is it going to be to make this down, drop the cost to make it more affordable for growers of all sizes and operations?
So I mean, so when we talk about the cost, so the robotic and automation system, there's some of them are actually is not in high cost. So for example, precision irrigation system is more kind of close to, I think, all scale of growers can use them. Of course, there's some of the robotic systems that has kind of certain kind of at this stage, they're still very costly. For example, using robotic system for picking apples. And those robotic systems can be very costly because it's involving a lot of parts and then a lot of techniques there. I believe there's two ways. One is actually kind of with the technology development, and also newer kind of like what I present using other type of robotic arms. For example, the Cartesian system can be much cheaper. But also there's some companies also provide service to the small growers. For example, they're lending them their equipment to the growers so they can use with a little bit cheaper price.
It's so as you said, a lot of the system sensors are being widely used, like for quantifying water use and using water more efficiently. That's not so costly. And you did show the robotic cow milking, which is still somewhat expensive, but a lot of people are finding that, especially with decreased availability of labor, the costs are affordable. More and more people are adopting robotic milking, even though it does, particularly some of the models do have a lot of moving parts and so forth. So it is picking up in some areas, particularly where there's enough demand. It makes it more profitable for companies to go into it. So, but it's hard to predict when. It'll always be a challenge. One of the questions I was asked, or we were asked, was, are there tests being done to compare crop production between the traditional agriculture and agriculture that use a lot of IoT, artificial intelligence, robotics, and so forth? Have there been many sort of studies to compare conventional systems with systems that start to adopt several of these technologies?
I mean, so there's some comparison work have been done for example, for the autonomous driving tractors, for example. If we are using that technology, how it can actually reduce the fuel use and also improve the efficiency. Those have been done. And for like special crops, for example, for harvesting, I think they're most studied right now still kind of in the research, for example, research stage. There's some comparison, but not in a kind of in a full scale, see how economically can be comparable to those to conventional way. But I do think that's for irrigation and spraying technology, there's the study has been compared to for the conventional and those precision techniques. So there's a lot of saving if we can use the precision technologies.
Yeah, I would participate in some of this research in Australia where it was very clear that the cost of sensors and automation systems were far less than the savings of water use that occurred. So that's an area where it does seem to be picking up. One of the questions, a specific question sent in the Q&A was how we're going on mechanical harvesting of mushrooms and how far away that is from commercialization.
So for the mushroom harvesting, there's, I mean, for processing mushrooms already like using the machines, especially in the European countries. So they're using, that is only for processing mushrooms. For fresh markets, there's, I think the research project is going on, and also there's some private company are developing some prototypes of testing right now. I mean, it's probably need some like, I think at least 5 years to see if there are any kind of compared to commercial commercial available for applications. So there's some challenge for mushroom harvesting is like the mushroom growing is pretty tight and also very fragile. So it's kind of, you need to be handled very gently. So there's something to concern. But of course, I think it's one thing is for mushroom harvesting is like they're growing in the indoor facility. So it's kind of a little bit compared to the outside field is a little bit more in the controlled environment. That is one advantage. So, I mean, there's study on that, and hopefully that robotic mushroom harvesting can be achieved pretty soon.
Right. One of the questions that also ask, are we able to touch on vertical farming techniques and technology as it relates to climate-controlled environments? And certainly I've seen considerable use of robotics and systems like that. And an advantage because it's a closed environment, vertical and so forth. Track technology can be used very efficiently because it's all there.
Yes.
So that seems to have considerable promise.
Yes. Yes, I talked to some folks on the like vertical farming and controlled environment farming. So there's, like you said, they're tracking like those kind of automation system actually can be a little bit more easier to be adapted in those kind of environment because your location of your crops and everything are fixed, and then you have better chance to apply those automation. There's another one is for those kind of facility. There's automation for the environment control. You have the for example moisture, temperature, and other kind of parameters to control.
Adjustment of lights, louvers,
yes, lighting system, everything. Yeah.
I should go back up a little bit and say that one of the challenges for mechanical harvesting of mushrooms for fresh markets in particular is even the least bit of damage will cause bruising and browning around those spots where that's occurred. There is a technology that's been developed here at Penn State that would address that. It uses the so-called CRISPR technology to introduce mutants in an enzyme called polyphenol oxidase that causes that browning reaction. And so in principle, if people were willing to adopt that CRISPR-based technology, that you could harvest it and the browning effect would be much reduced. So it's possible, in principle, it's possible to link the technologies.
Okay.
One of the other questions that was raised is how close are we to self-driving farm equipment where the farmer starts it, fills in the GPS coordinates and leaves? But we've already got that. We've already got some, so there are quite a lot of automated tractor systems are already being in use, right?
Yes. So autonomous tractors has been has been commercialized, so you can actually buy them. So those are like you can just set up a GPS, like the path, and then the location, destination, then the tractor will go there. And there's some other ground robots as well. They're either using the GPS or some are using even LiDAR to do the autonomous driving. So
yeah, that's so it's already, it's the example, it's already here and it's reasonably cost effective.
yes, I
The
think it's
the
affordable.
cost operating them, especially since they can run 24/7 without a driver. The labor costs can offset some of the equipment.
Yeah, the law right now, I think is they need to have a driver there, but I don't think that it's necessary to have driver on the seat. But then they just the law right now is kind of thinking the tractor still need a driver there.
Yeah.
Without what?
It's a bit like automated cars. There's still a sense most people would like to see a driver there just to be safe,
Yes.
just to be comforted. What about the power sources that can be used for these technologies? Are they driven by battery? Is it possible like solar, grid powered generators and so forth into the systems? What are some of the kinds of things people are doing about power sources? I think the question was also leading at renewable power sources.
Yes. So we can see that batteries and the solar panels are using more and more. So for a lot of equipment and also maybe a little bit small scale kind of vehicles, they're starting platforms. They're trying to use the battery and using solar panel charging. For the precision irrigation system, for example, that actually consume a very small power, and then that's can use battery and solar panel to charge. And for tractors, there's even have the battery driven tractors, and for the like ground robots as well. A lot of batteries are kind of battery driven options there. For some other kind of, I think there's still a lot of other equipment with using the generator or using the engines to drive, but I think a battery driven is kind of a good trend.
So presumably they've got a lot of lithium batteries that can keep the operation running for hours at a time, and the batteries themselves could last for a couple of years, something on that order.
Yeah, actually, I just talked to a small kind of a ground vehicle company, and they are, for example, their battery charge 8 hours. For example, they can run like 4 to 6 hours, something like that, and it's depend on. It's like I think the lifespans like depend on how many charging you use. And like for example, you give you 5,000, 6,000 charges for the lifespan or something like that. So I think the battery technology has been developing and improved. I think continue to do so.
Right. And one question to ask about what kinds of remote sensing or new technology in general as it relates to container grown stock. Well, certainly water sensing to have sensors that tell you when you really need water and not be flushing water or fertilizer out of the pots is a big one.
Yes. Irrigation and fertigation. I think that using fertilizer as well. Nutrient management. Those are very big part of
those kinds of high value, high intensity systems. Water and nutrient management by sensors is very much on the growth.
Yeah, those can be like you can do the automation and also can monitor those sensors remotely.
Yeah, great. What are the weather concerns? So these kinds of automated systems more or less sensitive to damage or wear and tear from weather-related events?
So I think first, for example, those sensors definitely need to be pretty sensitive, right? So in most cases, especially for the cameras, and then they need to be either covered or built with a rugged enclosure. So the weather condition, I think most of the, if we consider to commercialize product, that those should be not a big problem because they're going to make them next steady for use in very kind of harsh environment like agriculture environment is always not very good. So yeah, that's if that is going to be commercialized product, that won't be a very big problem. But weather conditions do sometimes affect the performance of the system sometimes. For example, if you have big wind, then the sprayer system won't be very accurate because the drift will be more during the wind effect, those kind of things. Yeah.
So another question was, are the different colors of fruit, for example, apple, blueberries, etc., a problem for the calibration of the robots?
No. So the color is just one of the feature. So sometimes if the color of the fruits is too close to the leaf, for example, that may be a little slightly kind of challenge. For example, if you have the green leaf and with red apples there, it's much easier. If you have green leaves and green fruits, then it's a little bit challenging. But also there's other features you can identify. If for example the shape, the cluster or something like that. So you still have different type of features can identify differential from fruits and other surrounding environment. So that's what I think the deep learning, like artificial intelligence, can help a lot of those things.
So the deep learning you're referring to goes back to having lots of pictures of the sorts of things you're looking for. The machine looks at, the computer system looks at many of these pictures and tries to work out algorithms that describe them, and then uses those algorithms to match up against unknowns. That's really what you mean by the deep learning?
Yes. So you kind of you need to have some data sets to train them. So you have labels. So you see this is a fruits by our recognition. So we see this is fruits, so we mark them. And later on, computer can learn and train them. And then eventually come up with a model that actually can automatically detect those objects later. So it's kind of train and learn process.
Yeah, so it's a mathematical model it uses that fits with what their sensors identify. Yeah. I just want to mention that years ago, people around the world started developing this kind of sensor technology for weed control, and particularly in Western Australia, for example, they could identify a particularly shaped weed that had sort of long leaves coming from a central spot called skeleton weed, and it had a unique appearance. And so what the sensors would do is look for that shape of a particular color against the soil, and they could make just a quick squirt of pesticide on top of that weed to try to control it. And a lot of economics, some of this dates back 20 years, they looked at the economics of it to try to figure out, coming back to these cost questions, what was the balance between saving enough on pesticide that would justify the additional expense of the sensors and the rest of the equipment. And the answer that came out of it is, if you were spraying, if the weeds were a relatively small part of the habitat, like 20%, maybe 30%, it could be highly cost effective. But once it got more than about 50% of the habitat, there was very little difference between just getting an ordinary sprayer and spraying everything, and the costs of creating a machine that might save 20 or 30% of the herbicide overall. So there's the economics has that kind of in it.
So that's actually come with a concept of treat earlier. So for the crop is the same, like we want to treat them earlier. We can want to do those tasks earlier before it's too late. Then at the early stage, you will see the difference. Of course, on the later, if the system already the tree already infected, then we need to spray anyway, right?
Yeah. So another question, Adrian's asked a question in the Q&A. Where might we be headed for the establishing and harmonizing system standards among supplier firms so that diverse systems can be integrated and continually updated with simple and uniform user interfaces? That is, I think they're looking, well, the question continues, thinking about the challenges for farmers and producers who are not sophisticated users and maintainers of such tech products. But I think what they're talking about is plug and play, like we've used to. If there were different kinds of systems, are very difficult for us as a consumer to mix parts that would play a CD and different speakers and so forth. So is there some kind of industry standardization that's occurring to make the plug and play work with a minimum of background information?
Yeah, I think this is a good topic, and also I think there's some discussion around a lot of places, like they're trying to see how to unify for example, the robot system, right? So if you have robots here, we don't need to actually to buy a new set of robots to do pruning compared to harvesting, for example, right? So the only part difference is like the end parts. So how we can actually easily to adapt to another small part to this whole common system, then we can use it for different work, like a tractor. So tractor is one good example. Like you can do anything. Like you can hold a kind of attach different kind of equipment on the back. So that's what the concept for robots as well. So eventually you have one set of robotic arm, and then you have a camera system, but then you have probably different end effector mechanism that I can easily to replace them. That can do, and also for other kind of crop monitoring system as well. If we have a sensor system, different sensors to measure, for example, soil moisture, or measuring the leaf vitalness or other kind of information from the field, if we can actually integrate all of them together, come with a single interface, have the multiple information, that will be also very good information for the growers just to easily to adopt.
I sort of imagine, like with robotic milking, that as more and more people have it, there'll be a greater market for new skill sets, new kinds of employment, where people as consultants or working for a company would be helping keep all these things running. So maybe in the future, instead of a geek squad, we'll be calling up the ag squad to come out and help us retune all of our robotics and sensor systems.
Yeah,
something we can hope for.
That's something good.
So you mentioned all your collaborators, that you had a number of collaborators working on things. And so that your collaborators include people who are pomologists, crop agronomists, entomologists, weed scientists, and so forth. But you have quite a strong group of engineers to back you up. You mentioned a few, such as Suat Ermak, the new chair of the department, and so forth. But you have a much broader skill set, because Penn State has such strong engineering skills in terms of people, not only at your other institutions, but here at Penn State you can draw on. How much scope is you picking up on that already? Look at some of the problems you have.
Yeah, I think that's I have been talking to the engineers from like electrical engineering. I listed one of the name there, but I think there's a lot of potential that actually can extend my research scope to more like sustainable agriculture aspect. For example, we can involve in the water management and other kind of like the environmental engineering. So those are big part of the precision ag. And what we do is trying to, for example, minimize those kind of impact, but how to evaluate, and then how to evaluate the performance, everything like that. So I think we need a big kind of extended group of people working together for large scale. Yeah.
So say it needs an extended family, but Penn State has a very strong College of Engineering that we can tap into when we need to. And some campuses, like the Barron campus up in Erie, as the whole campus has a strong focus on engineering. So Penn State collectively has got a lot of engineering skills. And it could, a real plus for Pennsylvania, probably because of the increasing drought problems faced by fruit and vegetable production areas in Arizona and California. There's a great opportunity for Pennsylvania to increase doing this, but hand in hand with that, or hand in operating tool, is that we really need to be able to address the labor costs of being able to do this if we're going to successfully expand the opportunities for fruit and vegetable production here in Pennsylvania. So this is clearly it's an important area for the college. And I should say that we're trying to recruit another colleague for you currently, right?
Yeah,
so
that is ongoing. Thank you for that.
Yeah, we're in the process of trying to hire a second engineer to work with Long and to expand the scope. So with that, I might wrap up for today. That it's I got to extend special thanks to Long for a great presentation joining us today, and for our audience. Before you log off, please make note of the next college sessions that'll be on your screen. If we can load those up on the screen, Mary and Mary. In July, we'll be learning more about avian influenza in Pennsylvania. In August, we'll be back at Ag Progress Days, where we'll host a town hall with Pennsylvania Department of Agriculture Secretary Russell Redding and myself. Then in September, we will learn more about the latest research and information on common ticks and tick-borne diseases in Pennsylvania. So I'm looking forward to having you join us for all those sessions and look forward to the next events. Thank you for being with us today and have a great afternoon.
Thank you. Thank you all.